Assalamu alaikum. Let's start our day. So we have waited for 30 minutes. Still, maybe more people are coming, but due to the time constraint, we cannot wait more. We have to start. I will request again, please come at 9 because we have lot of content to cover, and if we lose every day 30 minutes, we will then at the end of the day maybe not able to cover what we have planned. So yesterday we were when we left, we were discussing about the OpenFlow lab. So I will start again from the lab, and I would request everyone to please turn on your laptop if you have, and then log into the APNIC Academy, and we will start the lab. I have already completed the lab. I will just show you the demo, and but we do not have a time. I cannot give like maybe 30 minutes or 40 minutes. You to complete it, you have to do it at your own time, maybe after the workshop. But I will just show the demo, so it will be easy for you to follow the instructions and see what are the different options we have on the platform. And I hope that would be easy. But the other MPLS lab, that we will do together later in the day. So I have went to the courses, then virtual lab, and since I have already saved the lab, so it is showing me as a first option. Otherwise, you can search for the OpenFlow lab, and you will be able to see this lab. Then you need to click on the launch lab. I have already saved, that's why it's showing me continue. So if I will click it, then it will launch it. Remember, you need to disable the pop-up blocker for the APNIC Academy website. Otherwise, the new window, it will not open and you will not be able to see the lab interface. It went to the another screen, that's why I dragged it back. Let me see if I can duplicate the screen, because from here it's not easy for me to share and at the same time see it. You are having issue while connecting to the Wi-Fi. So can you try the other SSID, which is Serena? Okay, sorry, I was fixing the display. So initially when you will log into the lab, as I said yesterday, you will see the CLI on the left hand side, and on the right hand side you will see the instructions. So initially in your case, you will see like a blank page, and you need to move to the part 1. You will land here, and then you need to click at the bottom, which is the next on the right hand side, and after that you need to log into the mininet. So remember, we have 2 hosts in the lab. If you need to check like on which host you are currently, you will click in the center of the CLI, and you will see H1 Ubuntu ODL and H2 mininet. So if I will click on the Ubuntu, that means I have access to the Ubuntu or interface of Ubuntu. If I will click on the mininet, then it will switch the control and I will go to the mininet. Initially you will see there is it will ask for the prompt. You have to type the login, username and password. So the username is mininet and the password is mininet as well. After that you can execute the next commands. Like you can check the IP address. So the command is IP address show. It will display the IP address on the interface, and if it's not displaying the IP address, then you can set the IP address as well. Like you can assign the IP address 100. But if it's already assigned and then you try to assign it, it will give you an error. The other way to access the mininet is, if you have the IP address, you can go through the Ubuntu host as well. So how you can access through the Ubuntu host? You can open like a new terminal, and then you have to do the SSH. So how you can do it? You can see here we have command SSH mininet, and then you have to type the mininet IP. The IP is 100. So one way of typing the command is you can copy the command from here and go to the lightning button. From there go to the text, type text and type on the clipboard. After that, you can modify the command as well. Like in this case, I have to specify the IP address. So I will specify the IP address 192.168.1.100, and then you click OK, and it will paste the command. You can directly type the command as well, but if you are not very much familiar with the Linux, then copying command could be an easy way. So after that, it will give you the prompt for the password, and then you are into the mininet. So once you are into the mininet, then you can build the simple network. How you can build a network? If you give this command sudo mn-mac controller none. So what it will do, it will create a switch for you and 2 hosts, and these 2 hosts will be connected with the switch. But since we have specified controller is none, so it will not have any controller in this case. So after that, once you have executed this command, you can give the command nodes to display the nodes as well. So since I have not created any network, that's why it's not showing me. But on the other window, I have already created. So if I give the command here nodes, it will display me the list of nodes there as well. I'm just minimizing the extra window so you are able to see. So you can see if I am typing the nodes, it is showing me the nodes as well. Let me bring up the output so you can see it clearly. Maybe I have to drag it because it's at the bottom. So if I type the nodes, it's showing me what are the different nodes I have within the mininet, and even I can generate some traffic between the host. I can send the ICMP request. I can ping H1 from host 1 to host 2, and I can send 4 packets. Since in this case I have already enabled the controller, so it is showing me the traffic is moving on. But in your case, if you will do the part 1, there we have in the first exercise no controller, so when you try to execute, you will see the request timeout. So after that, you can exit it. If you want to just exit out of it, then it will destroy the network, and again you can enable the network using the controller. So if you will give this command again and specify the controller is equal to default, or you do not specify the controller parameter, then it will actually show you you have the network with the controller and communication will happen. Once you are through to this, you will be able to see similar output, and you will be able to ping the host as well. What we have in part 2? In part 2, we are going to install the Open Daylight controller, and after this, once you have installed, you can see there is a way to access the web interface for the controller as well, which is on you can access on port 8081. So I have already completed this step, and then I can see in my case, if I go to the host, and there if I try to access the controller interface, I can access it as well. So I have to type either the local host or the 127001, that is against the IP of the local host as well. I have to specify the port number, which is 8081, and then the index.html, and it will then show me the interface for the controller. Initially, it will ask you the username and password as well. But since I have logged in, so it is showing me the interface after the login. If you will click on the topology, initially you will see it is empty, because you have not, the controller has not received any information from the switch. So if it shows initially empty, that is totally fine. So it will show you the similar interface, just show you the switch, but then you can generate some traffic and click on reload. So once you will click on reload, it will show you the host, because when traffic moves on from the switch, then switch is able to share the information what it's learning with the controller, and the controller is able to give you the visibility of the network as well. You can click on the nodes and see what are the different nodes we have. Like in this case, it's showing us 3 nodes. And on which interfaces these nodes are connected as well, their MAC addresses we can see here. and the port numbers. So this is the lab. Actually, we have just as a proof of concept to show how you can use the OpenFlow and the Open Daylight controller to manage a switch. And you can see in this case we are able to know our network. The next part in this lab, which is like you can also do if you will have time, like you can access to the OpenFlow manager. So by accessing the OpenFlow manager, then you can add the entries or delete entries in the forwarding table as well. Like in the switch, we have the forwarding table, and we can change the forwarding table as per our requirement. So if I move on, so here if you will go to this part, then you can access the OpenFlow manager on the port 9000. Once you have access to this, then you can delete the entries and create some new entries as well. So there are some instructions. If you will follow, you will be able to do some of the actions. You can even block the communication between the host, and you then try to ping and see if it is working or not. And same, you can again bring back the network and normalize it and see the communication is happening. So whatever changes we do on the switch directly on the CLI, so in this case we can see we are able to do the same thing through the controller, and what different actions we want, we can achieve those as well. So as I explained earlier, due to the time constraint, I will not be able to give you the time to do this lab now, because it's already just 5 minutes left in the 10. So we have to move to the next presentation, but for sure we will do the LDP lab and the segment routing lab together. If you have any question regarding the lab, you can ask me now, or maybe if you have more if you need support, we can see it later on.
Sir, I have one question. OpenDay is an open source controller. Yeah, OpenDay. So we can add any devices on it, like firewall, router, switches, or some specific.
Like which vendors are supporting? Most of the vendors, they support the integration with the Open Daylight controller, and there is just maybe one command to just configure it. It's not a lengthy process. No, it will use the OpenFlow to communicate between the device.
The end device should support what protocol end device should support?
It should support the OpenFlow.
OpenFlow.
Because in this case we are using the OpenFlow for the communication.
So all the vendors support OpenFlow?
Mostly they support. We can check like on the vendor website what are the different protocols they support and how it could be integrated.
Okay, thank you.
Any other question? If there is no question, then I will move on to the next presentation we have. Yesterday I said that I will show you something regarding the controller as well. So just I have 4 slides about it, so let's go through it. This is just the definition like we already know. So as we know, through controller we can manage our network, and it provides a way to separate the control plane from the data plane, and the purpose is like to have the centralized management. So what are the more famous, or we can say the options we have for the open source controller? So these are the 4 open source controller available. One is the Open Daylight, another is the Open Network Operating System, and third one is the SDN framework and the Floodlight. If we see a comparison between them, so they have like what are the different capabilities and the protocols they support, and you can see in terms of features and support from the community as well. So I have the link for the documentation. If you need to know more about them, you can go to the documentation or their website. There you will be able to find the more information. This slide I will upload on the course material page as well, so then you will be able to access it. So the next we have is the segment routing. So we will before going to the segment routing, I will just refresh the MPLS concepts. So if you have like working on MPLS, that's fine. But if you are not, still it will be able to you will be able to sync with it, and you will be able to go through the concept we have, because the we are going to use the same concept in case of segment routing as well. So what is the the MPLS, if anyone want to define it, or how many people have worked on the MPLS? If you can please raise your hand, who are working or who have the experience of working on MPLS network. One. Anyone else? Okay, so I will try to go slow, so we have everyone is on the same page as. So as the name suggests, it is the multi-protocol label switching. In case of IP network, what we do is we do the forwarding based on the route lookup. Like when the device receive an packet, so it does IP lookup, and then it will match the destination address, and it will send the packet out of the interface from where it has received that route, or which interface has been selected to reach to this destination. And we have been doing this over the time, and it was working fine. But when we have more traffic on the IP network, or when more application or the demand was increasing, then the issue was how we can do it efficiently, because when you do the IP lookup, it takes time, and we want to have, in terms of performance, we want to achieve higher performance, or we want to use less resources and do the same thing. So then the idea came, okay, if we can do the same thing with having less processing, then the switching could be using the label switching. It could be one of the way. In that case, you will not do the lookup. You will just swap the labels and forward the packets. So as I said, the original motivation, we were doing the IP lookup, and then we move on towards the label switching. So what happened in this case? We were doing the lookup based on the IP and the longest match. We were doing when I am saying longest match, that means if we have a receive and destination traffic for a destination, and we will have maybe more than one entries in our table. So, but we will try to match which is more specific. If you have a /24 and /32, or maybe a /26. So it will see which one is the more specific. It's just to give you an example, if you are going to, if we exit from here and we need to go to maybe to another city. Okay, one road is saying this road goes to the specific city. Another is saying, okay, it is going to another city, and then from there you go to maybe multiple cities. So the road which is showing us the sign for that city, that becomes the more specific path to reach to our destination. But the other road, if this is not available, that could be the alternative way. Similar in case of routing lookup, we try to match the most specific, and if that is not available, then we take the alternative. And if still there is no entry, then we try to forward the traffic based on the default route. So this is how when traffic comes in, the router will do the lookup, and it will forward the packet because it has received the prefix through its interface 1, and then the next router, it will do the same, it will forward, and finally it will reach to the destination. But over the time, how the technology that has evolved, we have seen initially the MPLS, it was started in ITF working group around 1997, but it became very famous within few years, and even around after 2000, most of the service providers, they started deploying the MPLS, and they started providing the MPLS services. And we can see the large scale MPLS deployment, it was around 2006, and then mostly the service provider, they try to provide the layer 2 or layer 3 VPNs, and we kept on using it. And with the increased demand, like we keep on adding different applications like the video conferencing and even the cloud application, they are also on the MPLS as well. So whatever was coming, new services, we were trying to deliver using the MPLS, because this was one of the way to like deliver our services, and it was easy. Like we were using BGP, and then within BGP we can say we were using the multi-protocol BGP and trying to deliver the multiple services. So what MPLS was helping us, like it was decoupling the routing and the forwarding. Like the MPLS can allow the router to switch packet based on a simplified header. So in this case, once you receive the packet, traditionally you are just forwarding the data, but in this case the router, they can be better utilized by looking up just on the labels, not on the IP addresses. And the advantage was like it was taking less time to forward the packet. So how the switching happen in case of MPLS? We have the once the traffic comes in, we have the IP payload, we have the transport payload, and the actual payload as well. So the label switch router, it actually encapsulates the data in MPLS packets and then forward it. So it will put the MPLS header and then send towards the next destination. If we look it into the MPLS header, so we have the label which is 20 bits. We have the EXP bits which is used for the quality of service, and bottom of the stack, like what is the stack, this is your first label, second label, or third label. And then we have the TTL. TTL is similar to like the IP. So we have three operation in case of MPLS: push, swap, and pop. So once the traffic comes into the MPLS network, it adds the MPLS label. So we say this is the push operation. And after that, the packet goes to the next router. The next router, it will just swap the label, mean incoming label, it will verify, and then we'll see what could be the outgoing label. So it will replace the incoming tag with the outgoing tag. It's similar like you send some parcel to a company or maybe to an airline, and they see the tag, and then they put the corresponding tag to send to the next provider or maybe to next handler, whoever is it. So they can match the incoming tag and again take the appropriate action. Similar here, router actually see, okay, if I will receive the traffic with this tag, then it is the outgoing tag. So it has a mapping. So using that mapping table, it will just replace the tag and forward it. And we say this is the swap operation because we are swapping the label. Finally, once it reaches to the destination need to remove the label and then forward the packet, because the last router, once it removes the label, then it will be able to see what is the original packet inside and who is the receiver, because there could be a multiple host connected on the end router. And this operation is like the pop the label, we are removing the label. In terms of architecture, like we have the control plane and data plane, and where this MPLS fit in. So we need a protocol through which we can distribute the labels. So there are number of protocols which are used for the label distribution. And then we have within the control plane, we say lib, which is the label information base. And based on the lib, we actually forward to data plane the LFIB, which is used for the forwarding, for the actual forwarding of the traffic. And this is similar to IP forwarding as well. Like there we have the RIB and the FIB. Here we have the lib and LFIB. So we can see the label distribution protocol. They actually exchange the information with the label information base table, and then the information is also shared with the label forwarding information base as well, which is used for actual forwarding. So your packet, once it come in, the forwarding can happen based on the IP and based on the labels as well. So we have, in case of MPLS table, we have the next hop label forwarding entry. We have the ILM, which we say the incoming label mapping, and the FEC, which is used to forward the unlabeled packets, because if we receive unlabeled packet, then we see how we can forward them. In terms of node type, we have like different node type. The first one is the Ingress label edge router, which is your router which receives the packet, and this is your unlabeled packet, your normal IP packet. Once this ILER receives it, then it does the push operation. It will add the MPLS label. After that, the router in the middle, which could be your core router, they will just swap the label, and we can say these are the label switch routers. Once the traffic reaches to the end destination, which is the last router of the MPLS domain, and this is your egress label edge router, and this router will pop the label. So the first router, it will push, and the middle router, they will do the swap operation, and the last router, it will just do the pop and then forward the traffic. It will pop and see what is inside and then forward the traffic. So in terms of MPLS VPN type, if we see yesterday when we discussed it, like the P and PE routers. So again, the PE router, they are at the edge of the MPLS domain, and the PE router, these are the provider router, they are in the middle, and actually the customer is connecting with the PE router, and the PE router, they are just act as a core router and swap the labels. Our label switch path, like what is the path taken by the PE router to deliver the traffic, that's we say the label switch path, and it is established from both the PE routers, like the incoming, from where the traffic is coming and where the traffic is going. So how the label switch path is set up? So before we forward the traffic, we need to establish the LSP, and we can use different protocols for the label distribution. So we have the option to use LDP, and in that case, the forwarding is happening based on the shortest path. We have the RSVP. If you want to do the traffic engineering, you want to dictate the path, then we have to enable the RSVP. And if we want to provide the MPLS services, then we have to use the MPBGP. In terms of role, we have upstream and downstream router as well. So upstream, downstream router is where we have the destination, and it actually then advertise the label, and the upstream router, it receives the label and then sends the traffic. So the downstream router, it will advertise the destination with the label, and each of the router, it will receive, and it will create its own ILAM and then forward the label to the other router. So you can see here, once the R3, it receives the label 300, that becomes the incoming outgoing label, and from if the traffic is coming from the R3 side, then it will see, okay, traffic is received at 200, it will swap with 300 and send towards the R4. But from R2 perspective, it becomes different. The outgoing label is 200 and incoming will be 100. And on R1, the outgoing label is 100, because the traffic will, if it needs to send the traffic towards 192.0.2.4, it will send on the right hand side, not on the left hand side. From the left hand side, it will just receive the unlabeled traffic or the plain IP traffic. So once it has received the label, then every router, it will create its own ILM and just note down the label mapping and the IP corresponding IP address. So the BGP, as I said earlier, the MPBGP we use to deliver the VPN services, because the LDP will not be able to deliver the layer 3 VPNs. There is a way you can still deliver the layer 2 VPN without using BGP, but if you want to deliver the layer 3 VPN and other types of VPN, you have to use the BGP. So in that case, there will be two labels. One is your VPN label and the other is the transport label. So your VPN, every VPN you will configure, it will get one label. Based on that label, you will be able to identify your customer on the particular PE. Like here we can see one CE1 is attached to PE1. So in this case, when you configure the PE router for this customer, it will assign one label for the interface which is connected with CE1, and then all the traffic which is coming from the CE1, it will put that label. And on the other side, once we configure the remote end, which is PE2, so it will also like assign a label with the for the CE2, and both the routers, they will share this information with each other. So they will share, okay, I have this VPN and this is the label, and the other router will say okay, I have this VPN and the label is this one. So this is how the label information will be advertised for the which is assigned for the specific VPN as well. So in this case, it's advertising like label 1, 2, 3, 4 for the VPN service. So if we compare the MPLS with the IP, so in case of IP, the routing or forwarding was happening based on the destination, and we were using the forwarding table which was sent through the control plane, and again we have the TTL just to see if the traffic is remaining there roaming around. So once TTL becomes 0, then drop it. Similar for the MPLS, we are doing the forwarding but based on the label, and we are using the forwarding table learned from the control plane as well, which is like the LFIB, and we also have the TTL feature in this case as well. In case of IP, we run the routing protocols on the at the control plane level, but in case of MPLS, we run the routing protocol which actually help us to distribute the labels. In terms of encapsulation, like here we have IP header, but in case of MPLS, we have the MPLS header. QS is also supported in both cases in terms of like troubleshooting or management to check the connectivity. We can use ping and trace route. Similar in case of MPLS, we can use the ping and trace route. So how the ILM is built, the incoming label mapping. So let's see, once the PE2 routers, it will have the like incoming label of 100, and it will then advertise this to other routers like PE3 and to PE6 as well. So once PE3 receives this 100 label 100, it will create an entry like the outgoing label will be 100 and incoming label is 200. So then it will advertise 200 to PE2. So PE2, once it receives the label 200, it will also create an entry like the outgoing label will be 200, incoming is 300. And it will advertise the label 300 to P1, and P1 will also create its own entry for ILM, like the outgoing label 300, incoming label 400, and it will be advertised to all other routers like to P5, P1, and again the P5 will also advertise, and the P1 it will receive the label 400 through P1, and then it will create an entry. Maybe you have a question like P1 will receive 2 labels for the P2 because there are multiple paths. So based on the like its own algorithm, it will just select the one and keep the second as a backup. So now if it receives any traffic for the destination 192.0. The destination is 192.0.2.22, then it can use the label instead of the IP lookup. Similarly, P1, it will also advertise its own label, and all the router, they will actually receive it and have an entry within their ILM for the P1 as well, and this information will reach to the P2. So once both the P1 and P2, they have received the information, that means if they receive the traffic, or they need to send any packet to each other. So instead of doing the IP lookup, they can use the label switching, and then the router in the middle, they also have their ILM, so they can forward the traffic. Another thing is we need to notice, like in this case, we are LDP use the IGP protocol, which is like your OSPF or ISIS. So in this case, we are not doing any kind of traffic engineering. It will be up to the underlying network, how the different paths are available. So the routing will be based on the shortest path first. Like whatever is the shortest path, based on the IGP metric, it will take us. So in this case, you can see here we have the metric 100 here between P5 and P6. That's why it is taking the upper path, because this link is becoming undesirable because of the higher metric on it. Yeah, so as I said earlier, if you are receiving two labels, it will just select one as a best, and the second one it will just note as a secondary based on the metric, or it's run its own algorithm like the shortest path first, and it will select the one as a best one. So the loop avoidance is similar like we have in case of OSPF. So we select the one destination as a best, and second we list as a like standby or the secondary. The other thing is like we have the TTL. So once the packet moves on in the middle routers, if it's not reaching to destination, it will keep on decrementing the TTL. So once the TTL reaches to 0, it will just drop the packet. So it will not keep on moving there forever between one router and another router.
Can we use OSPF and ISIS in this topology? Because we're talking about a single autonomous system.
Actually, LDP need the support for the underlying protocol, which could be OSPF or ISIS. You need to have for sure, because in case of LDP, we actually use the loopback addresses, and you need the reachability of loopback addresses within your network. Because P1 and P2, they should have the, or even the other routers, like from P3, the P2, it will discover their loopback based on the IGP. So we need a routing protocol within our domain. It could be any of one like, but if you do not run, then you can do the static routing, but that's not an option in case of like the practical network, because you cannot have static entries for all the nodes, and if you need to add a new node, then we cannot, it will become unmanageable. So once we have built the ILM, then we need to forward the traffic. So how the traffic forwarding will happen? So once the traffic is received from C1, which is our customer in this case. So P1 router, it will receive the traffic. Then it will add the MPLS label, MPLS VPN label. So it will add the VPN label and then forward the traffic towards P2. So it will push two labels. Your first label is your VPN label, and second label is your transport label. So it is similar. You are sending the packet to someone else. First you pack it, then your courier will also put their own package or their own box on top of it. Because he is sending maybe to another city, there they will again just open up the outer box and see who is the receiver inside. And then they will send the packet. Similar, we are putting, one is like the identifier, the VPN label, which is for the enterprise traffic, just to identify like which customer it is. And the second one is your transport label. So the router in the middle, they will not check the VPN label. They will just keep on swapping the transport label. So let's see how it moves on. So this will be your payload. At the top, you will have the transport, then the VPN label, then the actual payload, actual traffic you have. So P1 will receive it. Which operation it will does? Remember we discussed 3 MPLS operation that a router can do. Push, swap. Yeah, so thank you. So it will do the swap because the first router is doing a push. So it will swap based on its ILM table. So remember, it has the incoming and outgoing label. So if incoming label is 400, so it will swap with the outgoing label, which is I think in this case is 300. So it will swap the 300 for 400 and send the packet with the new label towards PE2. Because PE2 knows what is 300, PE2 does not know what is 400. So once it receives, it will again do the swap operation and then forward the traffic towards the PE3. So in this case, PE3 will do again the swap and traffic reaches to PE2. Now PE2 need to do like two pop. It will pop the top label and it will also pop the VPN label. So first, before popping the VPN label, based on the VPN label, it will able to identify which customer is the receiver or who is the customer, because there could be more than 2 or 3 enterprises connected on the same router. So based on the VPN label, it will be able to identify the customer, and then it will look up in the specific table, because this VPN label will help him to identify, to look into a specific table, because there could be a multiple tables and each customer has their separate table, and it will look up the destination in the specific table and forward the traffic. So it will pop the VPN transport label, it will check the customer table based on the VPN label and then pop it and then forward the traffic to the CE. So using the traditional networks, either we have to create the IPsec or other things, but MPLS actually give us the way to deliver multiple services and using the same devices with maybe a simplified way and without creating any tunnel. So the tunnel is created automatically here, the label switch path, which I mean, and the traffic is forwarding based on the shortest path, because we are not specifying the path, the device itself is checking what is the shortest path to reach to the destination. So there is another concept which is PHP. So in this case, the earlier we saw the P3 router, it is doing this swap, but this idea came, okay, once it has reached to the one destination before the final destination, so this device does not need to swap the label, because eventually the PE2, it's going to pop the top label and then check the VPN label and pop it as well. So what is if this device does not swap, it just pop the top label and send the traffic with VPN label and the actual payload. Then the last device, it does not have to do 2 jobs, it just need to do 1 job. So this was the concept behind the PHP, the penultimate hop popping, it is said. So the last router before the final destination, it does not swap, it just pop the label. So this is how our 3 MPLS operation, these are done by the different router, like push, swap and pop. So it will not send any label, it will just send the null label instead of putting any label. So this is how it will build the ILM with the PHP support. And similar, once it receives the traffic, pop, swap, swap, and this will pop 200 and send traffic only with the VPN label. And then it will identify the VPN label and then pop it and send the payload. So this is like we are again optimizing, we are thinking, okay, this is another way to speed up the things and do it maybe in a better way. So in case of LDP, it follow the IGP path based on the OSPF or ISIs, and all the nodes, they will have the ILM, they will build the ILM, and a single LDP label which will be associated with the transport of the packet, and then the label, they are assigned by the downstream and sent towards the upstream router as well. So LDP label, it will keep on changing at each of the hop, and it is locally significant. That means the other routers, they may have this different label or same label, but the only that router where this label is, he knows what to do with it. If we want to do the traffic engineering, then we have to turn on another protocol, which is RSVP. So in this case, it will give us the ability to dictate the path. Because earlier we saw when we receive the traffic, it will follow the shortest path and then the traffic will be sent. But if we have a specific requirement, like all the traffic from P1 router to P2 should traverse or should go to P2, but avoid the P2 to P3 link. So we want to avoid P2 to P3 link, and we want to send the traffic from P1 to P2. So in this case, we have to build a tunnel which is avoiding this path. So first we have to, when we are building the tunnel, we send the RSVP T path message, and the other router, once it receives it, then it will actually reserve the bandwidth, and after that the LSP is built. So in order to create the specific path, we have to specify all the nodes which are coming in between, and this is done against the ERO, which is the object to record the path information. So we have to specify the path from the source to the destination, because we want to have the control over the path. So we are saying the first node will be P1, second node will be the P2, and then we are saying the third node will be P5, but after that we are saying the next node will be P6 and then P2. So this is how the path will be created, and all the nodes in the middle, they will be able to reserve the bandwidth as per the requirement, and then the traffic will follow this path. Because if we do not specify this path based on the metric, because here we have higher metric, traffic will go on the upper path. We want to avoid the metric, because based on the metric, if you put higher metric, then that path becomes undesirable. So if you want to do not want to use the traffic engineering, and then you have to maybe set equal metric on all the links, and then source and destination will see what is the metric from the upper path and lower path. If they are same, then both the path they could be used. Then it will be like a load sharing, or it could be the equal cost multipath as well. But here we have specific requirement, that's why we have to specify the path, and we have to turn on this RSVP. So once this path has been created, then again the ILM will be built. So the label mapping will be done. So similar, every router will create its label mapping, and then once the traffic will come, it will actually use the path. Every router is going to do the same operations, and finally your traffic will reach to the destination using the specific path. Number of reasons why we use traffic engineering. The first one is, like, all the paths in your network will not have the same bandwidth. So if we try to want to use all the links, all the resources, then we have to do the traffic engineering. Secondly, sometimes certain links have different latency. Like, just to give you an example, if we have a network between Karachi and Islamabad, okay, so one path is maybe we are going the shortest path, following maybe a motorway, there is a fiber going along the motorway. So this one becomes the low latency path. Another path may be going through Balochistan or other provinces. So you do not want to have both paths together, because you want to have some redundancy. If there is any cable cut or some other natural disaster happen, both of your cables, they are not destroyed, or you do not lose connectivity. So later on we have a customer who is saying, I need lowest latency path between these two cities. Okay, so if you want to give him keep his traffic on the lowest latency path unless that path is available, so you have to dictate the path. Otherwise you will not have the control.
Does not the metric and other protocols that are currently
so in case of
they do not resolve it.
In case of metric, you can control, but imagine if you have like more than two paths, and still you want to keep some of the traffic, because if you have 2 or 3 paths, all the traffic between the source and destination, it will follow the lowest metric path. So the problem what will happen, your other path they will be empty and they will be underutilized. And maybe you will face a congestion on this path. So now you need to shift some of the traffic to the other paths. So in that case, you have to go for the traffic engineering. Actually, the traffic engineering concept is not new. It was used in road or transport as well. I maybe read a paper from the 1960 time as well, and they were mentioned like they are measuring how much is traffic between two cities from the Jhelum to Islamabad, and which section they need to increase the lanes and these things. So even there, they use this concept.
I know it's very old, and in networking it's also very old. But practically, I haven't seen so many people using.
No, in all the ISPs, they are using the traffic
Okay,
engineering.
in the ISPs, okay.
Yeah, because they have the transport. In case of campus network, actually, maybe it's not required since you are within the same geography. But if you have multiple links and you are running your own MPLS network, there are even universities or organizations which are not like service provider, and they have their own MPLS network. Like I know in case of UAE, there the electricity company, they have their own MPLS network. So then for sure they are using like traffic engineering as well, because they can have multiple links as. I hope everyone will be clear on why we need the traffic engineering. Because we want to, the purpose is we want to use or take the maximum advantage of our resources. Okay, so let's, we were forwarding the traffic using the traffic engineering, and we can see it can take the specific path we are giving, and then it can reach. So the next we have the example of like if we have two nodes and we want to have the full mesh. That's mean how many paths we have. We have to create so many tunnels or so many policies. So we then can take advantage of these things. So this is like a downside of this. You have to create many things, and like it will be laborious for you. If you add a new node, obviously, if you want to take all the paths in consideration, you have to create so many tunnels between all the nodes. So this is like we have one path, then this could be, you have to create two tunnels, because if you create one tunnel, it will be just forwarding. For the reverse traffic, you have to create the tunnel from the other side as well. So it will not be happen automatically like in case of IPsec or other tunnel mechanism. You just create the tunnel and both endpoints, they come up. So same tunnel you can use for the incoming and outgoing traffic. But in case of RSVP, you have to create the tunnel from the both the direction, because each tunnel is just unidirectional. So that means just to use one path, you have to create two tunnels. And if you have like more than two paths, so just if we can see any to any reachability for 3 nodes, so we can see how many tunnel, like we will have to create 6 paths in that case. So if when your network is growing, it becomes a headache to add more tunnels, because it's a manual work. In case of if you do not have any like automated way, then you have to, whenever you are adding a new node and you see how many different destination or different other P routers it can talk, so you have to create all the tunnels between all those nodes. So if in case of 4 nodes, you have to create 12 paths. So the number of nodes increase, your number of paths, they are going to increase as well. Like for 5 nodes, you have to create 20 LSPs. Just to give you a comparison, like how many tunnels you can have. If you have like 100 routers in your network, you have to create like almost, it will be 9,900, which is near to 10,000 paths. So we'll see how in case of segment routing, we can do it like in an efficient way. So just we are saying like what is the downside of using doing it manually. So if you want to calculate for the number of nodes how many paths you need, so you can think of n into n minus 1. So this will give you the number of LSP you need to create according to your nodes or routers. So the final thought about the RSVP, it will allow you to create the path or dictate the path, and then you can avoid the shortest path, or you can avoid the path based on the IGP. But you have to like enable the RSVP on your all the nodes which are going to take part in the traffic engineering, the end node and the node in the middle as well. And all the nodes, they have to maintain the state for the RSVP, because nodes in the middle, they need to create the ILM, and they need to like reserve the bandwidth and then send the message to downstream router as well. And then the label will be changing at each of the node, and it has local significance. If we compare it with the LDP and BGP, so in case of LDP, we have low complexity. You do not need to create LSPs, you do not need to create path. You just turn on the, enable the LDP, and that's it. But in case of RSVP, you have to create the path as well. First, you need to note down, okay, which are different paths, what are the IP addresses, and then if you want to take a specific path and you want to avoid it, you have to, like, there is a way to do it dynamically as well. In case of RSVP, you just put dynamic like a keyword, so then it takes the IGP. But if you want to be very strict, then you have to specify each of the node. But if you want a mix and match, you can have few of the nodes as a like based on the IGP or open shortest path, and few of the path should be the explicit path as well. Label allocation, we can see point to multi-point, and in this case it's a point-to-point. Label significance is local. In case of LDP, you do not have traffic engineering, and RSVP you have the traffic engineering. Fast reroute, it works. So fast reroute is concept like when there is any failure within the network, and the node want to quickly recover or send the traffic on the alternative link, then you can enable the fast reroute. So it will try to repair it locally and use the alternative link to send the traffic on the available path. In terms of scaling, like in RSVP is complex because you have to create so many tunnels, but in case of LDP, it's easy. You will just add a new node, you will enable LDP, and label is distributed automatically. IGP interaction, so you have to, the RSVP actually, it requires the OSPF or ISIS extensions, and LDP also dependent on the IGP as well. So both of them, you have to run OSPF and ISIS, and then this is built as another protocol on top of that.